Okay, good evening. Welcome to Math for James 10, number 1. I wanted to make this movie about this really neat problem I saw on Twitter and how I thought about it today. Just to kind of talk through for myself. I've been thinking about some of these problems as I get back into math. But as I was going to make this movie, just to make sure I stated the problem exactly how he did, I realized for the first time all day didn't read the problem right initially. But this was still a cool problem, so I want to go through it just kind of more for laughs now. Because I was working on this all kind of in my head as I was driving up from Washington, D.C. to Stamford, Connecticut today. So it was made for a fun day. So here's the problem, the way I read it, which is wrong. I can walk along the x-axis at 4 miles per hour and anywhere else at 2 miles per hour. What is the shape of the points I can reach in 1 hour? So his problem was you can walk along the x and y axis at 4 miles per hour. But anyway, this is a neat problem too. So the first thing I said to myself, well, you can go 4 over in the x, 2 up in the y, so you're probably going to have this kind of diamond shape. And that was pretty neat, and then you start thinking about what this line is, and you can describe that shape. But then I realized that wasn't quite the right thing, because since you can go 2 up, one thing you're going to have around here is a circle like this. So you're going to be able to reach these points on the outside of the circle. So then I made the mistake of thinking that the shape was going to be outlined like this along the circle. Sort of a bumpy 4-leaf clover sort of pattern, I think is what someone kind of described it on Twitter, although they were not describing this exact shape, but this description sort of fits. So something like this. Now, I wasn't sure how to think about some of the other ways you might get to this funny little shape, so I started saying what happens if I go for time t over this way and then up at an angle theta here. And I got really into calculating, which is a terrible mistake by me, because now all of a sudden you remove yourself completely from the geometry and you start going over the board saying, okay, x is 4t plus 2 times 1 minus t cosine theta, y is 2 times 1 minus t sine theta, and off you go trying to do calculus or parameterize something, and it's just completely insane for such a nice, simple to state geometry problem to start calculating. But my mistake was once I started calculating, I couldn't stop. Because there's a much nicer geometry solution to this problem that only dawned on me tonight. And that is, the points you are going to be able to reach are going to be exactly the points where the line from the point 4 here is tangent to this circle. And somewhat incredibly, up here, if you find this point of tangency, you get a 30, 60, 90 triangle. And now you have almost kind of like an ice cream cone shape. Maybe 2 ice cream cones put together. And this 30, 60, 90 triangle emerges. So for a problem I misread, you actually get something pretty neat. I like this problem a lot. I like the problem he actually proposed too, where you would be able to go up 4 here, and then you get. Well, I'll let you work on that one. But this is kind of a cool problem. I'm actually very excited to be approaching some of this stuff on Twitter, seeing some really cool problems, finding some fun stuff to work on, some fun stuff for kids, and learning a little bit more about sort of the mathematical process and how you think about things. And so, to kind of wrap things up, this problem reminded me of one of my all-time favorite challenge problems that I'll try to write down here. The picture is worth 1,000 words on this. You are standing a distance of 1 unit away from an infinite plane. The edge of an infinite plane. So this is a cliff, and if you get to the cliff, you just sort of fall off. And the question is, you're blindfolded too, by the way, so you can't see. The question is, what is the minimum distance that you have to walk in order to, for sure, reach the edge of the cliff? This is kind of a cool problem. It's a cool geometry problem that's very, in my mind, similar to the one that I was working through today. I learned this problem when I was in much better mathematical shape than I am now, but still, it was a fun evening. So thanks for the problem, James.